The universe is not a static void, but a dynamic engine of continuous creation. Invisible forces sculpt entire galaxies, and cosmic engines rewrite the very laws of physics. We are made of star stuff, a truth that connects our existence to the grandest of scales. This video will reveal the 30 extraordinary mechanisms driving the evolution of the cosmos. You will gain a complete understanding of the invisible forces that dictate everything from the birth of a single star to the ultimate fate of all galaxies. What mysterious pressure is pushing the universe apart at an accelerating rate? How could a fleeting quantum event in the first second of time determine the location of every galaxy we see today? By the end, you will see the cosmos not as a collection of separate objects, but as a single, interconnected story of transformation. What does it mean to live in a universe that is constantly remaking itself? That initial burst of exponential growth solved some of the cosmos's deepest mysteries. Before the theory of cosmic inflation, scientists were puzzled by the universe's remarkable uniformity. Look in any direction and the cosmic microwave background, the faint afterglow of the Big Bang, appears almost exactly the same temperature. This presented a horizon problem. How could regions of the universe now separated by billions of light years, regions that could never have exchanged heat or information, possibly have reached the same equilibrium? It was as if countless strangers in a vast, dark room all independently decided to wear identical outfits without ever speaking. The only explanation was that these distant regions were once intimately connected, squeezed into a tiny, subatomic volume before inflation violently pushed them apart. This rapid stretching, faster than light itself, ironed out the cosmos, creating the smooth, flat universe we observe. The driving force behind this incredible event is thought to be a peculiar quantum field called the inflaton. This field possessed a strange property, a form of repulsive gravity that pushed space itself outward in an overwhelming surge. But this smoothing process was not perfectly perfect. On the smallest quantum scales, tiny fluctuations were inevitable. As the universe inflated, these minute ripples in the fabric of spacetime were stretched to astronomical sizes. They became the primordial seeds for all future structure, the slight over-densities where gravity would eventually get to work, pulling matter together to form the first galaxies, stars, and ultimately, us. The entire cosmic web we see traced across the night sky began as faint whispers in that first, unimaginable expansion. This foundational event did not just create a uniform universe, it created a universe with potential, a canvas with subtle texture ready for the next great artist to arrive. That artist would be gravity, and its first masterpiece was the formation of the very first stars. The subtle textures left by inflation were the starting blocks for gravity's grand race. But what if the very fabric of space itself holds a force that actively works against gravity's cosmic construction? This is the second extraordinary mechanism, dark energy acceleration. It is the baffling observation that the expansion of our universe is not slowing down but speeding up. Galaxies are being pushed apart at an ever-increasing rate, as if space itself is being stretched by an invisible, relentless hand. Nobel laureate Saul Perlmutter captured the essence of this mystery perfectly, noting that scientists are like detectives at a crime scene, piecing together clues from a universe that refuses to behave as expected. Primary clue came from studying distant stellar explosions known as Type 1, a supernova. Astronomers use these cosmic beacons, which have a known intrinsic brightness, to measure vast distances across the universe. They discovered that these supernovae were much fainter than their calculations predicted. The only logical explanation was that the space between us and those ancient explosions had stretched more than anyone had anticipated. The universe's expansion was accelerating. The leading theory points to a cosmological constant, a property of empty space that exerts a kind of negative pressure, pushing galaxies apart. This dark energy is not a minor player. It constitutes about 68% of the entire energy density of the cosmos. It is the dominant force shaping our universe's long-term destiny. One potential outcome is a cosmic scenario often called the Big Freeze. As acceleration continues unabated, galaxy clusters will be pulled beyond each other's observational horizons. The cosmic sky will slowly go dark, with all other islands of stars receding into an eternal emptiness. Some theories, like quintessence, suggest dark energy might not be constant but a dynamic field that could change over eons. What does this relentless push mean for the long-term evolution of everything we see? It paints a future where the grand structures forged by gravity are ultimately torn apart by the vacuum of space itself. Yet, to understand how those structures were built in the first place, we must descend from this vast, accelerating expanse to the smallest of scales, where the quantum world holds its own surprising power over the cosmos. Even the pure vacuum of space is not truly empty. It seethes with a faint, persistent energy, a quantum sea where particles and their antimatter partners flicker into reality for the briefest of moments before annihilating each other. These are quantum fluctuations, temporary changes in energy born from the Heisenberg uncertainty principle, which allows for such brief borrowings from the cosmic bank. The physicist John Wheeler poetically described this as space-time foam, a turbulent, churning landscape on the smallest conceivable scales. It is from this microscopic chaos that the largest structures in our universe were born. The near-perfect smoothness left by cosmic inflation was not entirely flawless. It was imprinted with these faint quantum ripples. Stretched to astronomical proportions during that rapid expansion, these tiny overdensities and underdensities became the primordial seeds for everything to come. They are the reason our universe is not a perfectly uniform soup of particles, but possesses the slight texture needed for gravity to begin its work. We can see the direct evidence of this quantum origin story mapped across the entire sky. The cosmic microwave background, that ancient afterglow, is not perfectly uniform. Its tiny temperature variations, millionths of a degree warmer or cooler in certain patches, are a direct imprint of those initial quantum fluctuations. These are the blueprints for the cosmic web, the slight gravitational wells where matter would eventually pool, collapse, and ignite the first stars. How is it possible that the faintest whisper from the quantum realm could dictate the placement of a galaxy a billion light-years wide? It is a profound connection between the smallest and the largest of scales, a reminder that the universe's grand architecture was written in a subatomic code. This code, however, required a powerful force to translate it into reality, a force that could sculpt those faint seeds into the brilliant structures we see today. That delicate balance, the faint overdensity born from a quantum ripple, is where gravity truly begins its work. It is the fourth mechanism, gravitational collapse, that transforms these subtle seeds into the brilliant structures of the cosmos. Picture a vast, cold cloud of gas and dust drifting for eons in the interstellar void. It is held in a fragile equilibrium, with the outward pressure of its own heat and turbulence barely counteracting the gentle, inward pull of its collective mass. But if a passing shock wave from a distant supernova compresses the cloud, or if the cloud simply grows dense enough through its own slow accumulation, that balance is shattered. Gravity gains the upper hand, and the cloud begins to fall in upon itself. This is the gene's instability, the point where gravity overwhelms all internal support, initiating a chain of events that forges new worlds. As the cloud contracts, it fragments into smaller, denser clumps, each one a potential stellar nursery. The core of each collapsing fragment heats up under the immense pressure, growing from a cold, dark cocoon into a warm, glowing protostar. We can witness this breathtaking process today in stellar nurseries like the Orion Nebula, where infrared telescopes peer through the obscuring dust to reveal infant stars, some still swaddled in their spinning disks of leftover material. Within these disks, microscopic dust grains collide and stick together, beginning the slow, patient construction of future planets. The great astrophysicist Subrahmanyan Chandrasekhar once reflected on the ultimate expression of this collapse, noting that the black holes of nature are the most perfect macroscopic objects there are in the universe. His words remind us that this relentless pull of gravity can lead to endpoints of incredible simplicity and power. But what determines whether a collapsing cloud becomes a single star, a binary system, or a black hole? It hinges on the initial mass of the cloud and the conservation of angular momentum, which flattens the infalling material into a disk and dictates the final architecture of a solar system. This gravitational collapse is not a chaotic crush, but a structured, physical dance. It is the universe's primary method of turning diffuse potential into concentrated, luminous reality. Yet, this collapse contains the seeds of its own regulation, for the most massive stars born from this process will live short, violent lives, ending in supernova explosions that blast material back into space, enriching the galactic environment and triggering the next round of collapse elsewhere. How does a collapsing ball of gas cross the threshold from simply being hot to becoming truly alive, to shining with the fires of nuclear fusion? The answer lies in the heart of the protostar, where unimaginable pressure and heat awaken a force even more powerful than gravity. Deep within the crushing heart of a protostar, a new and more powerful force awakens. When the core temperature soars past 10 million degrees, the chaotic dance of hydrogen nuclei overcomes their natural electrical repulsion. They slam together in a process called nuclear fusion, forging heavier elements and unleashing the energy that makes stars shine. This is the fifth extraordinary mechanism, the cosmic engine that lights up the universe. The physicist Arthur Eddington poetically described stars as the crucibles where lighter atoms are built into more complex elements. His insight was profound, for this stellar alchemy is what transforms the universe's simple primordial hydrogen into the rich diversity of matter we see today. In stars like our Sun, the primary process is the proton-proton chain. It is a step-by-step dance where 4 hydrogen nuclei are fused into one helium nucleus. With each completed fusion, a tiny amount of mass is converted into a colossal amount of pure energy, following Einstein's famous equation. This energy, released as gamma-ray photons, slowly works its way outward from the core, providing the outward pressure that halts gravitational collapse and stabilizes the star for billions of years. The sunlight that warms our planet and fuels nearly all life on Earth began its journey as a photon born from this fusion process deep within the sun's core. In more massive, hotter stars, a different and more efficient cycle takes over, the carbon-nitrogen-oxygen, or CNO, cycle. Here, carbon, nitrogen, and oxygen act as nuclear catalysts, facilitating the same overall transformation of hydrogen into helium but at a much faster rate. This is why massive stars burn so brightly and have such short lives. As a star ages, it exhausts the hydrogen fuel in its core. The core contracts and heats up even further, until it reaches temperatures high enough to begin fusing helium into carbon. This process continues in successive shells within the star, each layer fusing a heavier element, building a layered structure like a cosmic onion. In the most massive stars, this fusion chain progresses all the way to the creation of iron. But here, the stellar engine hits a fundamental wall. Fusing iron does not release energy, it consumes it. The star's central energy source suddenly vanishes, and gravity, held at bay for millions of years, wins the final battle in a catastrophic instant. The star is doomed, destined for a supernova explosion. How does the iron forged in a star's core, the ash of its nuclear furnace, become the material for future planets and life? The answer lies in the spectacular violence of the star's death, an event that scatters these newly forged elements across the galaxy. That final, desperate collapse of a massive star's core unleashes one of the most energetic events in the universe. A supernova explosion can, for a few glorious weeks, outshine its entire host galaxy, scattering the star's newly forged elements across the interstellar void. This is the sixth extraordinary mechanism, the cosmic forge that creates the very elements that make up our world and our bodies. Astronomer Carl Sagan captured this profound connection perfectly, reminding us that we are made of star stuff. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the heart of a long-dead star and blasted into space by its spectacular demise. These explosions come in two primary forms, each a unique kind of stellar death. The first is the core collapse supernova, the fate of stars more than about 8 times the mass of our Sun. When such a star fuses its way to an iron core, fusion stops generating energy. With no outward pressure to support it, the core collapses in less than a second from a structure the size of Earth to a dense ball of neutrons just a few miles across. The outer layers of the star, suddenly with nothing to support them, come crashing down at incredible speed, only to rebound off the rigid new neutron star in a colossal shockwave that blows the star apart. The second type, known as a Type 1, a supernova, occurs in binary star systems. A white dwarf, the dense Earth-sized remnant of a Sun-like star, steals material from its companion. If it accumulates enough mass to cross a critical threshold, it reignites in a runaway thermonuclear explosion, completely unbinding the star in a flash of light. Both types are cosmic recycling plants on a grand scale, but the core collapse supernova has one more critical job. The intense flood of neutrons in the explosion's aftermath allows for the rapid neutron capture process, or the R process. This is how the universe builds elements heavier than iron, like gold, silver, and uranium. Atomic nuclei are bombarded by neutrons so quickly that they cannot decay, gluing on more and more neutrons to create very heavy, unstable elements that then settle into stable forms. The beautiful Crab Nebula is a stunning example of this process in action. This expanding cloud of gas and dust is the remnant of a supernova that was observed on Earth in the year 1054. At its heart spins a pulsar, a city-sized neutron star that rotates 30 times every second, powering the nebula's glow. This celestial object is a testament to both the destructive and creative power of a supernova. What happens to all this enriched material blasted into the depths of space? These heavy elements are swept up by the shockwaves of subsequent supernova, mixing into vast clouds of gas that will one day collapse to form new stars, planets, and potentially life. The death of one star directly sows the seeds for the birth of future solar systems, a cycle of cosmic renewal that connects us directly to the most violent events in the universe. The death of a star does not always signify a final rest. Sometimes the dense remnant left behind, a neutron star, is destined for one last spectacular collision. Two such stellar corpses can become locked in a gravitational dance, slowly spiraling inward over millions of years. As they draw closer, they whip space-time itself into a frenzy, emitting ripples known as gravitational waves. The final moments of this cosmic spiral are breathtakingly violent. The neutron stars, each containing more mass than our Sun compressed into a city-sized sphere, slam together in a cataclysm that momentarily outshines every star in its galaxy. This is the seventh extraordinary mechanism, the neutron star merger, a cosmic alchemy lab that forges the universe's heaviest elements. The theoretical physicist Kip Thorne beautifully captured its essence, describing it as a crucible for creating precious metals. The collision unleashes a short gamma-ray burst, an intense flash of high-energy light, and is followed by a kilonova, an explosion 1,000 times brighter than a typical nova. The expelled material from this event is incredibly rich in neutrons, creating the perfect environment for the rapid neutron capture process, or R process. Atomic nuclei are bombarded by a dense hail of neutrons so quickly that they cannot radioactively decay, allowing them to rapidly build up into the heaviest elements in the periodic table. The gold in a wedding ring, the platinum in a catalytic converter, and the uranium that powers some nuclear reactors were all likely forged in the heart of such a cataclysm billions of years ago. In August 2017, the advanced LIGO and Virgo gravitational wave observatories detected the first confirmed neutron star merger, an event designated GW170817. This historic observation was not just a triumph of astronomy, it was a direct confirmation of cosmic alchemy. Follow-up observations across the electromagnetic spectrum revealed the signature of heavy elements being synthesized in the expanding kilonova cloud, proving that these mergers are primary cosmic foundries. How do these events shape the chemical diversity of the universe? A planetary system that forms from a cloud enriched by a neutron star merger will contain a richer blend of heavy elements. This chemical diversity could influence the very composition of its planets, potentially creating worlds with abundant precious metals or the radioactive elements needed to power geological activity and mantle convection deep within a planet. These violent endings for stellar remnants thus become essential beginnings, seeding the galaxy with the raw materials for complex chemistry and perhaps for life itself. From these intense, localized forges, we must now expand our view to the grandest structures of all, the vast cosmic webs and galactic engines that govern the flow of matter on the largest scales. These invisible magnetic threads form the eighth extraordinary mechanism, the galactic dynamo. A galaxy is not just a collection of stars, it is a colossal engine generating immense magnetic fields that weave through interstellar space. The astrophysicist Eugene Parker poetically called magnetic fields the skeletons of the universe, and for good reason. They provide an invisible scaffolding that shapes how galaxies evolve. This dynamo effect works because a galaxy is filled with a swirling, electrically conductive fluid, primarily ionized gas. As the galaxy rotates, this motion, combined with turbulent churning from supernova explosions, acts like a natural generator. It converts the kinetic energy of spinning gas into powerful magnetic energy through a process of electromagnetic induction. Think of it as a cosmic version of a bicycle dynamo, but on a scale of thousands of light years. The spiral arms of a galaxy like our own Milky Way play a crucial role, acting like lanes of concentrated motion that further twist and amplify these magnetic fields. We can observe these colossal structures using radio telescopes, which detect the faint radiation emitted by electrons spiraling along the magnetic field lines. These maps reveal a vast, intricate network of magnetism that guides the flow of cosmic rays, high-energy particles traveling at near light speed. The galactic magnetic field acts as a containment grid, preventing these rays from simply escaping into intergalactic space and instead directing them throughout the galaxy. This has a direct impact on the very birth of stars. These magnetic fields exert pressure on the giant molecular clouds where stars form. They can either help support a cloud against its own gravity, slowing down star formation, or they can channel flows of gas, triggering local collapses that lead to new stellar nurseries. How do these invisible cosmic force fields shape the long-term destiny of an entire galaxy? Their subtle push and pull influences where stars can be born and how energy is distributed across the vast galactic disk. Yet, to fully understand the architecture of a galaxy, we must look beyond the luminous stars and magnetic fields to an even more dominant and invisible presence. The luminous disk of a galaxy, with all its stars and swirling gas, represents only a tiny fraction of its true substance. Vera Rubin's meticulous observations of galaxy rotation revealed a profound mystery. She found that stars far from the galactic center were moving much too fast for the gravitational pull of all the visible matter to hold them in orbit. The only explanation was an immense, invisible presence, a vast halo of dark matter providing the gravitational glue that keeps galaxies from flying apart. This is the ninth extraordinary mechanism, the dark matter halo. These halos are colossal structures composed of hypothetical particles that do not emit, absorb, or reflect light, yet they dominate the mass of every galaxy and cluster. Their gravitational influence is the primary architect of cosmic structure, forming an invisible scaffolding upon which ordinary or baryonic matter can collapse to form the galaxies we see. The distribution of this dark matter within a halo is often described by what scientists call the Navarro-Frenk white profile, a universal density pattern that starts dense in the center and becomes more diffuse in the outer regions. We can map these unseen halos through their gravitational effects, most strikingly in a phenomenon called gravitational lensing. The immense mass of a dark matter halo warps the fabric of spacetime around it, bending the light from more distant galaxies like a cosmic magnifying glass. The Bullet Cluster provides one of the most direct and compelling pieces of evidence for dark matter's existence. This system is actually two clusters of galaxies that have collided. Observations show that the hot, visible gas from the clusters detected by X-ray telescopes was slowed down and separated from the bulk of the mass, which was mapped through gravitational lensing. This proves that most of the matter is dark, passing through the collision unaffected while the visible gas interacts and gets left behind. Supercomputer simulations of the universe show how these cold dark matter halos merge and accumulate over billions of years, building the cosmic web we observe today. The greatest remaining mystery is the fundamental nature of the particle itself. What is dark matter made of, and how can we detect it directly here on Earth? This invisible architecture not only dictates the form of galaxies, but also sets the stage for the most powerful engines in the universe, whose brilliance can be seen from the farthest cosmic shores. The vast, invisible halos of dark matter provide the cosmic scaffolding upon which all luminous structure is built. This leads us to the 10th extraordinary mechanism, the formation of the universe's large-scale structure. The cosmos is not a random scatter of galaxies, but a magnificent, intricate web. Enormous filaments of dark matter and galaxies stretch across billions of light years, connecting at dense nodes to form massive clusters, while between them lie vast, nearly empty cosmic voids. Cosmologist John Einasto perfectly captured its significance, noting that the universe is not random. It has a structure that tells us about its history. These patterns are a direct fossil record of the primordial universe, the amplified echoes of those initial quantum fluctuations. The growth of this cosmic web is a story of hierarchical clustering, a bottom-up assembly where small galaxies and dark matter halos, drawn together by gravity, merge over time to build ever larger structures. This gravitational sculpting was not unopposed. In the early universe, ordinary matter was a hot, ionized plasma, tightly coupled with light. The intense pressure from photons created powerful sound waves that rippled through this primordial soup. When the universe cooled enough for atoms to form, allowing light to travel freely, these waves were frozen in place. This event, known as baryonic acoustic oscillations, imprinted a preferred scale on the cosmos, a standard ruler of about 500 million light-years that we can still see in the clustered distribution of galaxies today. Massive redshift surveys like the Sloan Digital Sky Survey have meticulously mapped this structure by measuring the distances to millions of galaxies. Their work reveals colossal formations like the Sloan Great Wall, a filament of galaxies over 1 billion light-years long, one of the largest known structures in the observable universe. Meanwhile, dark energy plays a paradoxical role. While it dominates the universe's energy budget, its repulsive effect actually slows down the growth of these structures by pushing matter apart, counteracting gravity's relentless pull. Supercomputer simulations, such as the landmark Millennium Run, have successfully modeled this entire cosmic evolution, showing how the subtle seeds from the Big Bang grow into the web we observe, confirming our understanding of the underlying physics. How do these vast arrangements influence the flow of cosmic energy? These cosmic filaments act as gravitational highways, channeling gas and galaxies toward the dense clusters at their intersections. It is within these intense, crowded nodes that we find the universe's most powerful and energetic phenomena, where gravity and extreme physics combine to create engines of unimaginable fury. At the heart of many galaxies, a titanic struggle unfolds between creation and destruction. The 11th extraordinary mechanism, active galactic nuclei feedback, reveals how the most voracious objects in the universe also act as cosmic regulators. A supermassive black hole, millions or even billions of times the mass of our Sun, can become an active engine when it pulls in vast quantities of gas and dust. This infalling material forms a searingly hot accretion disk, and as it spirals inward, it releases phenomenal amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. Astronomer Sandy Faber profoundly noted that black holes are not just endpoints, they are active players in shaping galaxies. This dynamic role is feedback, a process where the energy output from this accretion heats surrounding gas or drives it entirely out of the galaxy. This expulsion or heating of the raw material for star formation effectively suppresses the birth of new stars, putting a brake on the galaxy's growth. The most dramatic displays of this power are the relativistic jets, narrow beams of plasma accelerated to nearly the speed of light that can punch through intergalactic space for thousands of light-years. The giant elliptical galaxy M87 offers a stunning example, with its famous jet visible even to amateur telescopes, a cosmic blowtorch emanating from its central black hole. There is also a mysterious and precise correlation between the mass of a galaxy's central black hole and the properties of its surrounding stellar bulge, suggesting a deep, co-evolutionary link where the black hole's growth and the galaxy's star formation history are intimately connected. These outflows can have impacts far beyond their home galaxy, heating the intracluster medium, the thin, superheated gas that fills the spaces between galaxies in a cluster. How does this feedback maintain balance in cosmic ecosystems? In massive galaxies, it acts as a thermostat, preventing runaway star formation that would otherwise consume all available gas too quickly. This self-regulation ensures that galaxies mature into the diverse forms we see today. Yet, the release of such colossal energy often involves a sudden and violent reconfiguration of invisible lines of force, a process where magnetic fields snap and reconnect, converting immense stored energy into heat and particle acceleration in an instant. These invisible magnetic skeletons can suddenly snap, unleashing pent-up energy in a spectacular flash. This is magnetic reconnection, the 12th extraordinary mechanism driving cosmic evolution. Across the universe, in the searing plasma of stellar atmospheres and the hearts of galaxies, magnetic field lines become twisted and stressed. When they cross, they can break and reconnect into a new, lower energy configuration, a process that converts immense stores of magnetic energy into explosive heat and powerful particle acceleration. The space physicist James Dungy rightly identified this as the fundamental driver of space weather. The physics hinges on what scientists call a current sheet, a thin, volatile layer where magnetic fields of opposing direction are pressed together. Early models, like the Sweet-Parker mechanism, described a slow, diffusive process, but the observed speed of events like solar flares demanded a faster theory, leading to the Petschek model, which includes a much smaller diffusion region and allows for far more rapid energy conversion. We witness this cosmic power on our own sun. A single solar flare is a monumental release of energy, equivalent to billions of hydrogen bombs detonating at once. This fury is born from the sudden reconnection of magnetic fields in the sun's corona. These events can hurl colossal clouds of plasma, known as coronal mass ejections, toward Earth. When these clouds interact with our planet's magnetic field, they can trigger brilliant auroras, but they also pose a risk to satellites, power grids, and astronauts. The same fundamental process is at work far beyond our solar system, in the powerful winds from pulsars and in the relativistic jets screaming from active galaxies. Magnetic reconnection is thought to play a crucial role in accelerating particles to nearly the speed of light. How does this rapid energy release shape environments across the cosmos? It acts as a cosmic pressure valve, transforming the slow build-up of magnetic stress into sudden, brilliant outbursts that heat entire stellar atmospheres and seed space with high-energy particles. The ability of a plasma to suddenly reorganize its magnetic fields and release such fury is a reminder that the universe is not just a place of slow, gravitational evolution, but also one of sudden, transformative flashes. To understand the origin of the very fields that make such reconnection possible, we must journey back to the universe's first fleeting moments. That delicate imbalance between matter and antimatter, a 1 in a billion asymmetry, is the reason anything substantial exists at all. This is the 13th extraordinary mechanism, baryogenesis, the process that tipped the cosmic scales in favor of matter. In the universe's first moments of unimaginable heat and density, matter and antimatter were created in nearly equal amounts. Had they been perfectly balanced, they would have completely annihilated each other, leaving behind a sea of radiation and nothing more. Our universe of galaxies, stars, and planets would never have formed. The physicist Andrei Sakharov identified the 3 essential conditions needed to create this vital imbalance. The universe had to be out of thermal equilibrium, a state where processes could proceed in one direction more favorably than another. There had to be interactions that violated the conservation of baryon number, essentially allowing the total amount of matter to change. And crucially, there had to be a violation of both charge and parity symmetry, known as CP violation. This means that certain particle reactions proceed at a slightly different rate than their mirror image antimatter reactions. It is this tiny bias etched into the laws of physics that allowed a small surplus of matter to survive the Great Annihilation. One leading theory, called leptogenesis, suggests this asymmetry may have first occurred among ghostly particles called neutrinos. These neutrinos, through their decays in the early universe, could have created a slight leaning toward matter, a preference that was then transferred to the familiar protons and neutrons we are made of through processes involving hypothetical transitions called sphalerons. The evidence for this primordial preference is all around us. We live in a world made almost entirely of matter, with very little primordial antimatter observed anywhere in the cosmos. Experiments like those at the Large Hadron Collider continue to search for the specific sources of CP violation that could explain our existence. How did this fundamental breaking of symmetry, a slight preference for one type of particle over its mirror, become the foundation for all cosmic structure? This profound question leads us directly to another of the universe's most fundamental and puzzling symmetries. The universe's preference for matter over antimatter was not the only symmetry broken in its youth. As the cosmos expanded and cooled, it underwent a profound transformation, a phase transition that irrevocably defined the laws of physics we experience today. This is the 14th extraordinary mechanism, spontaneous symmetry breaking. Imagine the early universe as an unfathomably hot and energetic state where all the fundamental forces were unified into a single, perfect symmetry. As temperatures plummeted, this symmetric state became unstable, much like superheated steam condensing into water. The system had to settle into a new, more stable, but less symmetric arrangement. Nobel laureate Peter Higgs speculated on the existence of fields that could break symmetry, a theoretical leap that led to the eventual discovery of the Higgs boson. This process is elegantly captured by a simple analogy. Think of a pencil perfectly balanced on its tip. This state is symmetric, identical from every direction, but it is also highly unstable. The slightest perturbation will cause it to fall, choosing one specific direction and breaking the symmetry. The universe did the same thing. In the electroweak phase transition, a scalar field known as the Higgs field acquired what physicists call a non-zero vacuum expectation value. This means that even in the emptiest reaches of space, this field has a constant background value. Its activation spontaneously broke the symmetry between the electromagnetic and weak nuclear forces, splitting them into the two distinct forces we recognize today. This breaking had a monumental consequence. Particles that had been racing around at the speed of light, massless and free, suddenly began to interact with this omnipresent Higgs field. This interaction is what grants fundamental particles like quarks and electrons their mass. Without this mechanism, there would be no atoms, no chemistry, and no structure in the universe. The theoretical underpinnings involve Goldstone bosons, particles that arise from broken symmetries and are eaten by other particles, giving them mass and transforming them, as seen with the W and Z bosons that carry the weak force. The implications ripple through cosmic history, potentially driving the inflationary expansion of the universe and influencing the very process of baryogenesis that made our existence possible. How do these broken symmetries, frozen into the fabric of reality, influence the evolution of cosmic structures? They created a world with mass, with distinct forces, and with the potential for complexity. This foundational shift set the stage for the next great actor to enter, an entity so fundamental that its very ripples can warp the cosmos. The immense gravity of a galaxy cluster does far more than just hold stars in orbit. It warps the very fabric of space around it into a colossal lens. This 15th mechanism, gravitational lensing, transforms massive cosmic objects into natural telescopes, revealing hidden details of the distant universe. Albert Einstein's general theory of relativity predicted that light would not travel in a straight line when passing through a gravitational field, instead following the curvature of spacetime. This was first confirmed during a solar eclipse in 1919, when stars near the sun's edge appeared slightly out of position, their light bent by our star's gravity. Today, we see this phenomenon on a galactic scale, where the gravity of a foreground galaxy cluster can bend and magnify the light from galaxies far behind it. This cosmic trick of the light comes in several forms. Strong lensing creates multiple, distorted images of a single background galaxy, or can even stretch its light into a perfect circle known as an Einstein ring. Weak lensing, on the other hand, produces subtler, statistical distortions in the shapes of countless background galaxies, allowing scientists to map the distribution of dark matter. Then there is microlensing, a temporary brightening of a star caused when a compact, invisible object like a planet or a black hole passes in front of it, its gravity briefly focusing the star's light toward us. The Hubble Space Telescope has provided stunning examples of this, capturing beautiful Einstein rings that act as cosmic magnifying glasses, letting us peer at galaxies otherwise too far and faint to see. What secrets of dark matter can this phenomenon unveil? By analyzing how light is distorted by galaxy clusters, astronomers can chart the invisible dark matter halos that provide most of the gravitational pull, creating detailed mass maps of the unseen cosmic scaffolding. This same principle of warped spacetime, which allows us to map the invisible mass holding the universe together, is also the very tool that revealed the universe is being torn apart, leading us directly to the discovery of dark energy and its relentless, accelerating push. Frozen in the faint afterglow of creation is a detailed blueprint for the entire cosmos. These cosmic microwave background anisotropies are the 16th extraordinary mechanism, a snapshot of the universe at just 380,000 years old. George Smoot beautifully called this radiation the baby picture of the universe, a fossilized imprint of its infancy. This ancient light reveals a nearly uniform sea of radiation, but it is punctuated by tiny temperature variations, mere millionths of a degree, that map the primordial density fluctuations. These subtle hot and cold spots are the result of sound waves rippling through the early universe. Before this epoch, the cosmos was a searing, opaque plasma where light and matter were locked in a constant tug of war. Photons pushed outward with intense radiation pressure while gravity pulled matter inward. This created a rhythmic oscillation, a booming echo trapped in the primordial fluid. When the universe cooled enough for neutral atoms to form, a pivotal moment called recombination, the photons were suddenly set free. They decoupled from matter and streamed across the universe, their patterns frozen in time. We can analyze these patterns through a power spectrum, a graph that charts the size of these temperature fluctuations against their angular scale on the sky. The first and most prominent peak in this spectrum is a monumental discovery. Its position reveals that the universe is geometrically flat, a key prediction of cosmic inflation. This single data point confirms that the cosmos we inhabit operates on the rules of Euclidean geometry, where parallel lines never meet. The subsequent peaks tell an even richer story. The second peak tells us about the strength of those early pressure waves, while the third peak gives us a direct measure of the density of dark matter. This invisible substance, which does not interact with light, still exerted its gravitational pull, sculpting the oscillations we observe. Missions like the Planck satellite have mapped these anisotropies with breathtaking precision, providing our most stringent constraints on the composition of the universe. The specific patterns we see are only possible with the precise amounts of dark matter and dark energy we have measured. How do these ancient ripples inform us about the universe's fate? They are the initial conditions from which everything evolved, setting the stage for the gravitational collapse that would eventually form galaxies. The precise balance of ingredients read from this cosmic barcode points toward a future of continued acceleration and expansion. To understand how the structures predicted by this blueprint actually took shape, we must move from this primordial calm to the most chaotic and energetic frontiers of the modern universe. 17th mechanism, accretion disk physics, reveals the final, brilliant blaze of matter before it vanishes from the visible universe. This is the fate of gas and dust that spirals into the gravitational well of a black hole or neutron star, forming a searingly hot, flattened vortex of plasma. Astrophysicist John Hawley rightly identified these structures as the engines of active galaxies, for they are cosmic power plants that convert gravitational potential into staggering amounts of light. The process begins when material, drawn inward by immense gravity, cannot fall directly in. It possesses too much angular momentum, forcing it to settle into a rapidly rotating disk. Within this disk, particles rub against each other, creating intense friction and magnetic turbulence. This viscosity, often modeled by the alpha disk prescription, acts as a cosmic brake, allowing the gas to shed its orbital energy and spiral slowly inward. As the material marches toward the event horizon, it is compressed and heated to millions of degrees, causing it to glow with intense X-ray and gamma-ray radiation. The brilliant light of a quasar, visible from the far reaches of the cosmos, is the thermal scream of this annihilated matter. For different feeding rates, the disk structure changes dramatically. At high accretion rates, we see a thin, efficient disk, brilliantly described by the Shakura-Sunyaev model, that radiates away its energy as light. At lower rates, the flow becomes advection-dominated, like a thick, bloated cloud where the heat is swallowed by the black hole along with the gas. The environment around the famous black hole binary Cygnus X1 provides a perfect laboratory. Here, gas stripped from a massive companion star forms a classic accretion disk, its inner regions heating up so intensely that they emit the powerful X-rays we detect from Earth. But these disks are not merely passive radiators. Their intense rotation and internal magnetic fields can launch and collimate bipolar jets, narrow beams of plasma accelerated to nearly light speed that punch out across interstellar space. How does this brilliant engine influence the growth of the supermassive black holes at the heart of galaxies? The rate and manner of accretion directly dictate how quickly these cosmic monsters gain mass, tying the luminous output of the disk directly to the evolution of the galaxy itself. This interplay between swirling matter and invisible magnetic fields is the key to understanding the most powerful and persistent engines in the cosmos. These cosmic rays are subatomic bullets, protons and atomic nuclei hurtling through the void at nearly the speed of light. This relentless, invisible rain constitutes the 18th extraordinary mechanism, cosmic ray acceleration. It is a process where charged particles are boosted to staggering energies by some of the universe's most violent events. The physicist Enrico Fermi brilliantly theorized that magnetic clouds in space could act as natural particle accelerators. His insight led to what we now call diffusive shock acceleration. Imagine a particle caught in the turbulent magnetic field of a supernova shockwave. It bounces back and forth across the shock front, as if trapped between two converging walls. With each crossing, it gains a little more energy from the motion of the magnetic mirrors, eventually being flung into interstellar space with a significant fraction of light speed. This process can produce particles with energies far beyond anything achievable in human-built colliders like the Large Hadron Collider. When we chart the number of cosmic rays arriving at Earth against their energy, we see distinct features known as the knee and the ankle. The knee, around 1 quadrillion electron volts, may mark the point where our galaxy can no longer confine the most powerful particles. The ankle, at even higher energies, could signify the transition to cosmic rays born in distant, active galaxies. Supernova remnants, like the beautiful Cassiopeia A, are prime suspects for generating the bulk of galactic cosmic rays. Their expanding shock waves provide the perfect environment for this relentless acceleration. We can also look to the Crab Nebula's pulsar wind nebula, a dynamic region where a rapidly spinning neutron star blows out a wind of charged particles, accelerating them to produce the nebula's characteristic synchrotron glow. But what is the ultimate impact of this invisible bombardment? These high-energy particles constantly strike planetary atmospheres, contributing to ionization processes that can influence cloud formation and even potentially affect climate patterns over long cosmic timescales. They also drive complex chemistry in interstellar gas clouds, helping to form the molecular building blocks of stars and planets. What do these subatomic messengers, forged in stellar cataclysms, tell us about the fundamental laws that govern all of reality? Their incredible energies provide a unique testbed for physics, probing the stability of the universe's most basic ingredients and the constants that define them. The very laws of physics that govern our universe may not be set in stone. The 19th extraordinary mechanism, the variation of fundamental constants, proposes that the bedrock numbers of reality could be slowly shifting over cosmic time. Imagine the fine structure constant, often denoted by the symbol alpha, which controls the strength of the electromagnetic force. This number dictates how atoms hold together and how stars burn their nuclear fuel. If it were even slightly different in the distant past, the entire history of cosmic evolution would be rewritten. The renowned physicist Paul Dirac was struck by curious numerical coincidences between cosmic and atomic scales, leading him to speculate that these constants might not be constant at all. This idea suggests that what we perceive as fixed laws could be local bylaws, temporary conditions in our corner of a much more dynamic cosmos. The driving force behind such a profound shift could be a slowly evolving scalar field, permeating all of space and subtly altering the fundamental couplings over billions of years. This is not just a philosophical curiosity, it has testable consequences. Scientists search for evidence by studying the light from incredibly distant quasars. As this light passes through ancient clouds of gas, it creates an absorption spectrum, a barcode that reveals the atomic properties of the early universe. Meticulous analyses of these barcodes have hinted at minuscule changes in the value of alpha, though these results remain hotly debated within the scientific community. Other crucial tests come from the process of Big Bang Nucleosynthesis. The precise abundances of the light elements forged in the universe's first few minutes are exquisitely sensitive to constants like the strength of the strong nuclear force and the proton-to-electron mass ratio. The fact that the observed abundances align so well with predictions places incredibly tight constraints on how much these constants could have varied. What would it mean for stellar evolution if nuclear reaction rates were different in the past? A slightly stronger electromagnetic force could make stellar cores burn hotter and faster, shortening the lives of massive stars and altering the schedule for enriching the cosmos with heavy elements. The potential for varying constants is a cornerstone of many attempts to create a unified theory of physics, often involving hidden extra dimensions whose properties change over time. If the fabric of reality itself is this fluid, It forces us to reconsider not just the history of the cosmos, but the nature of its underlying geometry and connectedness. The very geometry of our universe might be far stranger than we can directly perceive. This 20th mechanism, cosmic topology and multiverse concepts, explores the possibility that the cosmos could have a finite, yet unbounded, shape, or that it is just one of countless bubbles in a vast multiverse. Cosmologist Max Tegmark elegantly categorized these ideas into levels, from the simple realization that distant regions of our own expanding space are forever beyond our view, to the staggering concept of a mathematical multiverse containing all possible structures describable by equations. One compelling topological candidate is the Poincare dodecahedral space, a model where the universe, like a video game world, wraps around on itself. In such a cosmos, if you could travel in a perfectly straight line for long enough, you would eventually return to your starting point from the opposite direction. Scientists search for evidence of this by looking for matched circles in the cosmic microwave background, identical patterns on opposite sides of the sky that would be the ghostly imprint of the universe folding back on itself. So far, data from missions like the Planck satellite have found no such signature, placing tight constraints on these exotic shapes and suggesting our universe is most likely geometrically flat and infinite. Yet, the multiverse idea finds fertile ground in the very theory that explains our universe's uniformity, cosmic inflation. Eternal inflation suggests that the rapid expansion of spacetime is a never-ending process, continually spawning new bubble universes where inflation has stopped, each with its own random set of physical constants and laws. This connects directly to the landscape of string theory, a theoretical framework that proposes an astronomical number of possible stable vacuum states, each corresponding to a different universe with different properties. This leads to the anthropic principle, a reasoning that if countless universes exist with varied laws, we naturally find ourselves in one rare enough to allow for the emergence of galaxies, stars, and life. What would definitive evidence for a multiverse mean for our understanding of reality? It would transform cosmology, suggesting that the fundamental constants we measure are not deeply necessary, but merely local and accidental. This profound shift in perspective, from a single, unique cosmos to a potentially infinite ensemble, forces us to reconsider the nature of existence itself and the very flow of time and causality that we take for granted. Our cosmic view is permanently bounded by a fundamental limit. The 21st extraordinary mechanism, causal structure and cosmic horizons, defines the ultimate frontier of our knowledge. These are not physical walls, but boundaries in spacetime set by the finite speed of light and the relentless expansion of the cosmos. They dictate which events can ever influence one another, carving the universe into separate domains of causality. The most familiar of these is our particle horizon, the spherical edge of the observable universe. Every galaxy, every star, and every photon of the cosmic microwave background that we can possibly detect lies within this bubble. The light from objects at this horizon has been traveling for nearly the entire age of the universe, 13.8 billion years, just to reach our telescopes. This shell of ancient light represents the absolute limit of our direct observation, a final frontier beyond which we cannot see. Stephen Hawking's profound work on black hole event horizons finds a cosmic cousin in this concept. A cosmological horizon defines a point of no return for information, not from gravity but from expansion. As the universe accelerates, distant galaxies are pushed beyond our Hubble radius, the distance where their recession velocity equals the speed of light. They cross a threshold, fading from view forever, their light no longer able to overcome the stretching of space. This creates a future horizon, an ultimate isolation where vast regions of the cosmos will become forever inaccessible to us. This very limitation once posed the great horizon problem for cosmology. How could the universe be so uniform if distant regions had never been in causal contact? Cosmic inflation provided the elegant solution, suggesting that the entire observable universe was once a tiny, causally connected patch, violently stretched to a macroscopic scale. The light from the cosmic microwave background is a perfect illustration. It arrives from a spherical shell at our particle horizon, offering a snapshot of the universe at a mere 380,000 years old. We are, in a very real sense, looking at the inner surface of our cosmic bubble. How do these horizons shape our understanding of cosmic evolution? They impose a fundamental limit on how much of the universe we can ever know, and they define the playing field upon which all structure must form. This profound connection between information, causality, and the geometry of spacetime points toward an even deeper mystery, one that suggests the information content of a volume of space may be encoded on its bounding surface. This is the holographic principle, a radical idea that bridges our understanding of cosmic horizons with the quest for a theory of quantum gravity. At scales a billion times smaller than an atom, the smooth fabric of spacetime dissolves into a seething, chaotic froth. This is the domain of quantum gravity, the 22nd extraordinary mechanism, where the rules of the very large and the very small collide in a theoretical frontier. Our current understanding of the cosmos is fractured, with Einstein's general relativity governing the cosmic dance of planets and galaxies, while quantum mechanics rules the bizarre world of particles. Unifying these two pillars of physics is perhaps the greatest challenge in modern science, a quest to describe gravity itself as a quantum force. The physicist Carlo Rovelli beautifully captured the essence of one leading approach, describing space not as a static stage but as a network of relations, a dynamic weave of discrete loops. This is the vision of loop quantum gravity, where spacetime is granular, composed of tiny, indivisible units at the Planck scale. This fundamental graininess suggests that the dreaded singularity at the heart of a black hole, or at the beginning of the Big Bang, might not be a point of infinite density, but merely a place where our classical equations break down and a new quantum reality takes over. One profound implication of this is the concept of a big bounce. Instead of a universe emerging from a singular nothingness, it could be one phase in an endless cycle, with a previous cosmos contracting to an incredibly dense state before quantum gravity effects cause it to rebound into our own expanding universe. The theoretical foundation for such ideas often involves the Wheeler-DeWitt equation, a daring attempt to describe the entire universe as a quantum wave function. This equation famously lacks a time variable, suggesting that time itself may be an emergent property, a cosmic illusion born from the changing relationships between quantum components. How could we ever hope to test such an abstract concept? The answer may lie in the oldest light we can see. Subtle imprints from these pre-Big Bang phases or from the primordial quantum foam could be faintly etched into the patterns of the cosmic microwave background. Future observatories with exquisite sensitivity might one day detect these whispers from the Planck epoch, revealing the true quantum nature of our cosmic origins. This exploration of the universe's most fundamental architecture naturally guides us to consider how these same quantum processes set the stage for the chemical richness that followed. A galaxy is not just a collection of stars, it is a vast chemical refinery, endlessly processing its raw materials. This is the 23rd extraordinary mechanism, galactic chemical evolution. Over billions of years, the pristine hydrogen and helium from the Big Bang are gradually enriched with heavier elements, forged in stellar furnaces and scattered by violent deaths. The pioneering astronomer Beatrice Tinsley fundamentally changed our perspective, demonstrating that galaxies evolve chemically as they age, their composition a living record of their star-forming history. The entire cycle is governed by a few key factors. The initial mass function dictates the proportion of small, long-lived stars to massive, short-lived stars that are born, setting the schedule for element production. The chemical yields, the specific elements expelled by different events like core collapse supernova, and the gentle winds from aging asymptotic giant branch stars add their unique signatures to the mix. And all of this is regulated by grand flows of gas, with fresh, unenriched material flowing in from the cosmic web, while powerful galactic winds, driven by supernova or active black holes, can blow enriched gas clear out of the galaxy. We can read this chemical history book in our own cosmic backyard. The age-metallicity relation in the Milky Way's disk shows a clear trend. Older stars generally possess fewer heavy elements, while younger stars like our Sun are born from gas that has been cycled through many generations of stars. By analyzing the subtle lines in stellar spectra, astronomers can measure the precise abundance of dozens of elements in a star's atmosphere, revealing its origin story. A compelling piece of evidence lies in the chemical pattern of our own solar neighborhood. The specific mix of elements found here suggests that our solar system did not form in isolation. Its composition carries the imprint of one or more nearby supernova explosions that seeded the natal cloud with freshly synthesized material just before the Sun ignited. How does this chemical diversity influence the potential for life? It sets fundamental constraints. Too few heavy elements and rocky planets like Earth may not form. Too many, and the delicate balance of planetary atmospheres and chemistry could be unstable. This cosmic chemistry, written across the galaxy, guides us to consider another invisible force that shapes the flow of the very gas from which stars are born. These faint magnetic threads are not confined to galaxies alone, but stretch across the unimaginable voids between them. Intergalactic magnetic fields are the 24th extraordinary mechanism, a ghostly presence woven through the cosmic web itself. While incredibly weak, these fields are pervasive, existing in the vast, empty filaments and voids that separate galaxy clusters. Astronomer Philip Kronberg rightly observed that magnetic fields are everywhere in the universe, a truth that extends even into these near-perfect vacuums. Their origins are deeply mysterious, possibly seeded in the universe's first moments by processes like inflation or early phase transitions. Over cosmic time, these faint seeds were likely amplified by the powerful outflows from active galaxies and the turbulent motions generated as the large-scale structure of the universe formed. We can measure the strength and structure of these invisible fields indirectly through a phenomenon called Faraday rotation. As polarized radio waves from distant quasars travel through a magnetized plasma, their plane of polarization slowly rotates, a subtle twist that betrays the presence and strength of the magnetic fields along the line of sight. Observations of diffuse, large-scale radio emissions from galaxy clusters confirm that these magnetic fields truly do permeate intergalactic space. One of their critical roles is in confining and guiding the relentless flow of cosmic rays. These high-energy particles, accelerated by supernova and other violent events, spiral along the magnetic field lines that stretch between galaxies, their paths dictated by this invisible cosmic lattice. This confinement influences where cosmic ray energy is deposited, which can subtly affect the pressure and temperature of the tenuous gas in cosmic filaments, thereby influencing the rate and location of future galaxy formation. Upcoming observatories like the Square Kilometre Array are designed to map these faint intergalactic fields with unprecedented precision. using the Faraday rotation of millions of distant radio sources to trace the magnetic skeleton of the entire cosmic web. What can these ancient, pervasive fields tell us about the universe's earliest conditions? Their very existence and structure are a fossil record, potentially preserving information from epochs before the first stars ever shone. This grand, magnetic tapestry connects all cosmic structures, but it is within the isolated hearts of the most massive stars that another, final form of alchemy awaits, a process that forges the elements of life in a single, spectacular finale. The Sun will one day become a silent, Earth-sized diamond adrift in the void. This is the fate of all stars like our own, a gradual transformation into a white dwarf. These stellar embers no longer generate new energy through fusion. They simply glow with the intense heat left over from their former lives. As astronomer James Liebert described them, white dwarfs are the fossils of stellar evolution. They are cosmic clocks, cooling at a predictable rate that allows us to read the ages of the oldest stars in our galaxy. The process begins violently, with the star expelling its outer layers to form a beautiful planetary nebula. What remains is an incredibly dense core of carbon and oxygen, so compressed that a single teaspoon of its material would weigh as much as an elephant here on Earth. This tiny, searing hot sphere then begins its multi-billion-year journey toward absolute cold. The initial cooling is rapid, driven in part by the emission of ghostly neutrinos that carry energy away without interacting with matter. But the most fascinating phase occurs much later, deep within the white dwarf's heart. Under unimaginable pressure, the carbon core begins to crystallize, arranging itself into a solid lattice. This process of crystallization releases latent heat, a final burst of energy that slows the cooling dramatically, much like a lake releasing heat as it freezes over. Astronomers use detailed cooling curves, which chart a white dwarf's temperature against its age, to turn these objects into precise chronometers. The oldest white dwarfs we observe in ancient globular clusters have provided a key constraint, helping to pin the age of the Milky Way galaxy at around 13 billion years. This timeline aligns beautifully with the overall age of the universe, offering a powerful, independent check on our cosmic history. Yet not all white dwarfs fade away quietly. Their existence is governed by a critical threshold known as the Chandrasekhar limit. If a white dwarf in a binary system pulls enough material from its companion to exceed this mass limit, it triggers a cataclysmic Type 1, a supernova, a titanic explosion that completely unbinds the star. How do these fading remnants, these cosmic clocks, connect to the most energetic explosions in the universe? Their quiet, predictable cooling sets the stage for their own spectacular demise, a transition from a slow, steady fade to a sudden, brilliant flash that seeds the cosmos with newly forged iron. The death scream of a massive star can outshine its entire galaxy for a few fleeting seconds. These gamma-ray bursts are the 26th extraordinary mechanism, the universe's most powerful and focused explosions. They flash into existence without warning, a torrent of high-energy photons that can briefly outshine every star, quasar, and supernova combined. Astronomer Neil Gehrels helped reveal the diversity of their origins, linking them to the most violent endpoints of stellar evolution. There are two distinct species of these cosmic blasts. Long-duration bursts lasting more than 2 seconds are born from the core collapse of rapidly spinning, massive stars. As the star's core implodes into a newborn black hole, the infalling material forms a vortex of superheated plasma. This accretion process powers a pair of relativistic jets, narrow beams of matter accelerated to more than 99.9% the speed of light. If one of these jets is pointed directly at Earth, we witness a long gamma-ray burst. This is the collapsar model in action, a stellar death that produces not a spherical explosion, but a focused cosmic blowtorch. The brilliant event known as GRB 130427 provides a perfect example. Detected in April 2013, it was one of the brightest and most energetic bursts ever recorded, linked to a supernova in a relatively nearby galaxy. Its lingering afterglow, visible for days across X-ray, optical, and radio wavelengths, gave scientists an unprecedented look at the physics of these jets. Short-duration bursts lasting less than 2 seconds have a different origin. They are the final, fiery signature of two neutron stars merging, or a neutron star being consumed by a black hole. The collision ejects material rich in neutrons, creating the perfect conditions for the rapid neutron capture process, forging a significant portion of the universe's heaviest elements like gold and platinum. What do these fleeting flashes tell us about the cosmos? Their incredible brightness makes them beacons visible from the farthest reaches of space and time. By analyzing their light, we can probe the era of reionization, when the first stars and galaxies lit up and burned away the cosmic fog. They serve as cosmic yardsticks, helping to measure the geometry and expansion history of the universe itself. The very existence of these bursts and the elements they forge depends on the precise cosmic recipe, a balance of matter, energy, and the initial conditions set at the dawn of time. The precise balance of our cosmic density is a razor's edge between eternal expansion and fiery collapse. This is the 27th mechanism, the omega parameter, a single number that weighs the entire universe against its own gravitational pull. The fate of everything hinges on whether the actual density of the cosmos is above or below a critical value. If the density is too high, gravity will eventually win, pulling all matter back together in a cataclysmic big crunch. If it is too low, the universe will expand forever into a cold, dark emptiness. Cosmologist Jim Peebles highlighted a foundational truth, noting that the universe is very close to critical density. This near-perfect balance is a stunning confirmation of the theory of cosmic inflation, which predicted a universe so stretched that its geometry would be flat. The total omega parameter is a sum of its parts. We have omega m, the density of all matter including the dark matter that binds galaxies, and omega lambda, the density of dark energy that pushes the universe apart. Observations from distant supernova, the detailed patterns in the cosmic microwave background, and the vast maps of galactic structure all converge on the same answer. The total omega is incredibly close to 1, meaning we live in a flat universe poised on this cosmic knife edge. The Planck satellite's meticulous measurements have pinned this value down with extraordinary precision, leaving almost no room for a significantly curved cosmos. But this balance is not static. Over the deep history of the universe, the relative influence of these components has dramatically shifted. In the early epochs, matter dominated, and gravity's pull was slowly putting the brakes on cosmic expansion. Then, a few billion years ago, dark energy took over, and the expansion began to accelerate. How does this evolving tug-of-war shape the long-term evolution of the cosmos? It dictates the ultimate fate of all structure, determining whether galaxy clusters will remain gravitationally bound or be torn apart by the accelerating void. This delicate initial condition, set in the first moments of time, was the essential precursor for the next great act of cosmic construction, the forging of the very first atomic nuclei from the primordial fire. Within the universe's first 20 minutes, a brief and brilliant fire forged the first atomic nuclei. This 28th mechanism, Big Bang Nucleosynthesis, set the initial chemical composition for everything to come. The pioneering physicist George Gamow and his colleagues correctly envisioned the early cosmos as a primordial nuclear reactor. During this fleeting epoch, the entire universe was hot and dense enough for nuclear fusion to occur everywhere at once. Protons and neutrons collided and combined, building the universe's first complex matter from the primordial soup of hydrogen. The process was a frantic race against the expansion and cooling of space itself. As temperatures plummeted, nuclear reactions froze out, locking in the abundances of the lightest elements. The most significant product was helium, making up about 25% of the universe's ordinary mass by weight, with hydrogen constituting nearly all the rest. This prediction and its stunning confirmation by observation stands as one of the great triumphs of modern cosmology. The process also produced trace amounts of other light nuclei, including deuterium, a heavy form of hydrogen, and lithium. These tiny abundances are not mere footnotes, they are incredibly sensitive cosmic probes. Deuterium acts as a precise baryometer, its primordial abundance telling us the density of ordinary matter in the early universe. If the density of protons and neutrons had been much higher, nearly all the deuterium would have been fused into helium. If it had been much lower, almost none would have been destroyed. The fact that measurements of deuterium in ancient gas clouds, observed through the absorption lines of distant quasars, align perfectly with the baryon density derived from the cosmic microwave background, is a powerful validation of our entire standard model of cosmology. These primordial element abundances also place tight constraints on the particle content of the early universe. The number of light neutrino species, for example, directly influenced how quickly the universe expanded and cooled, which in turn affected how much helium could be synthesized. Any deviation from the predicted amounts would point to new physics, perhaps the existence of exotic, unknown particles from the cosmos's first seconds. What do these ancient atomic relics tell us about the universe's first moments? They are a fossil record from a time before stars, confirming the hot, dense origin of our cosmos and providing a pristine baseline from which all later chemical evolution began. This initial, nearly uniform distribution of matter, however, was not the final word, for gravity would soon begin to sculpt it, pulling matter into great clusters and leaving behind vast, empty expanses. Between the great walls and filaments of the cosmic web lie the true titans of emptiness. These are cosmic voids, the 29th extraordinary mechanism, vast regions of space nearly devoid of galaxies that are expanding faster than the universe itself. They are not simply empty, they are active participants in cosmic evolution, their growth driven by a profound gravitational deficit. While gravity pulls matter together in the dense filaments and clusters, it has the opposite effect in these underdense regions. With so little mass to hold them back, the space within voids stretches more rapidly, causing them to grow larger and emptier over billions of years. Astronomer Laura Mersini-Houghton has studied these empty domains as key tests of multiverse ideas, seeing them as potential windows into the initial conditions set by inflation. Their sheer scale is difficult to grasp. The Boötes void stands as a stunning example, a spherical expanse roughly 250 million light-years across that contains only a handful of galaxies, where a typical region of that size would hold thousands. This immense emptiness makes them perfect natural laboratories for studying dark energy. By carefully mapping the shapes and distribution of countless voids, scientists can measure how their expansion rate has changed over cosmic history, providing one of the cleanest probes of dark energy's influence. The subtle imprint of these growing voids can even be found in the oldest light we see. As photons from the cosmic microwave background travel through an expanding void, they lose a tiny amount of energy, a phenomenon known as the integrated Sachs-Wolf effect. This creates specific cold spots in the microwave sky, a direct link between the largest structures and the first light of the cosmos. Supercomputer simulations reveal a dynamic life cycle for these voids, showing them merging with one another in a slow-motion dance, much like the inverted image of galaxy clusters forming. How do these expanding bubbles of nothingness influence the grand architecture of the cosmic web? Their outward pressure helps to sculpt the surrounding filaments, compressing matter and guiding the flows that feed galaxy clusters. These vast empty regions are not mere absences, but active sculptors of the universe's visible structure, their relentless growth painting a clear picture of the dark energy that will dictate our cosmic destiny. This brings us to the final, overarching mechanism that ties all the others together, the ultimate fate awaiting our universe. Every structure, from the grandest galaxy to the most fragile atom, is destined to fade. This 30th and final extraordinary mechanism, the heat death and cosmic future, charts the ultimate fate of our universe, a slow journey into darkness driven by the unyielding second law of thermodynamics. This law dictates that entropy, a measure of disorder, must always increase in a closed system. Over unimaginable eons, all the energy gradients that power stars, galaxies, and life itself will be exhausted, leaving the cosmos in a state of maximum entropy, a cold, dark, and uniform equilibrium. The physicist Lord Kelvin was among the first to contemplate this sobering idea, recognizing that even the universe's vast energy reserves are finite. In our modern understanding, dark energy's accelerating push makes this outcome nearly inevitable, relentlessly diluting the cosmos and stretching it toward this final state. The timeline for this process is almost beyond human comprehension. After trillions of years, the last stars will flicker out, leaving the universe to the fading embers of white dwarfs and neutron stars. Over periods measured in googolls of years, a 1 followed by 100 zeros, even these remnants will cool to near absolute zero. Black holes, once thought to be eternal, will slowly evaporate through a quantum process predicted by Stephen Hawking, radiating away their mass until they too vanish in a final, faint puff of particles. What remains is a thin, ever-cooling sea of radiation and isolated subatomic particles, drifting further and further apart in an eternal, silent expansion. This bleak portrait is not the only possible future. Some theories suggest dark energy could intensify, leading to a big rip, where the accelerating expansion becomes so violent that it tears apart galaxies, stars, planets, and even atoms themselves in a final, catastrophic instant. Yet, even within this seemingly final equilibrium, the seeds of new beginnings may lie dormant. The theory of eternal inflation suggests that our universe might be just one bubble in a vast, eternally inflating multiverse, where new universes with different physical laws are constantly being born from the quantum foam of the parent space. What meaning can we find in a cosmic story that ends in silence and cold? This journey through 30 mechanisms reveals a universe of breathtaking dynamism, from its quantum origins to its grand structural evolution, all interconnected in a single, unfolding narrative. The heat death is not a negation of this story, but its final, logical chapter, a testament to a cosmos that lived, changed, and forged complexity against all odds before returning to a state of rest. These 30 mechanisms are not separate threads, but an intricate cosmic tapestry woven together across time and scale. From the faintest quantum whisper seeding a galaxy to the silent, relentless push of dark energy, they form a single, coherent story of transformation. Each piece interlocks, revealing a universe that is profoundly self-regulating, where the end of one process becomes the raw material for the next. A supernova's violent death scatters heavy elements into the void, enriching the gas clouds that will one day collapse into new stars and planets. At the same time, the ferocious energy from a galaxy's central black hole heats surrounding gas, preventing runaway star formation and imposing a cosmic balance. It is a dynamic interplay of creation and destruction, a feedback loop that maintains equilibrium from stellar nurseries to galactic clusters. The great physicist Stephen Hawking reminded us that the universe does not behave according to our preconceived ideas. Its complexity humbles us, urging a deeper appreciation for the interconnected dance we are only beginning to understand. This grand narrative is visible in the universe's largest structure, the cosmic web. Its vast filaments and voids are not random, but the direct descendants of the microscopic anisotropies imprinted by cosmic inflation, their patterns amplified by gravity over billions of years. How can this unified view of cosmic evolution inspire future discovery? Recognizing these deep connections allows us to see the cosmos not as a collection of isolated phenomena, but as a single, evolving system. It guides our search, suggesting that the key to one cosmic mystery may lie in the behavior of another, seemingly distant mechanism. This holistic perspective is the true legacy of our journey, a map that reveals how every part of the universe, from the smallest particle to the largest cluster, is part of a continuous, unfolding story. This intricate cosmic tapestry, woven from 30 threads of creation and change, reveals a universe in constant conversation with itself. We have witnessed how dark energy's relentless push dictates our long-term fate, how quantum ripples in the void blossomed into galaxies, and how the life and death of stars forged the very elements of life in a perpetual cycle of renewal. These are not separate tales, but interconnected chapters of a single grand narrative. The cosmos operates as a vast, self-regulating engine, where the explosive feedback from a galactic core governs the birth of new stars, and where the silent growth of a cosmic void sculpts the filaments of the web. Carl Sagan's timeless words remind us that somewhere, something incredible is waiting to be known. This is the enduring invitation of the cosmos, a call to look up and continue the search. Let this journey deepen your wonder. How does seeing the universe as one interconnected story change your perspective on our place within it? Share your reflections in the comments below. If unraveling these mysteries with us has ignited your curiosity, subscribe for more journeys to the frontiers of space and knowledge. Thank you for exploring the extraordinary mechanisms of our evolving